Okay, guys, good morning. I'm having a great time at district office, I'm sure. Probably not, but I'd rather be with you. However, that is not possible. So this will be the closest we can be to being together. So today's lesson is on types of reactions. So like we said yesterday, all of those equations you've been doing can be categorized into some groups or types of reactions. These ones that we're going to do are not all of them. It does not encompass every single type of reaction that's out there, but it is the major types of reactions that you are going to be using and be classifying. It still uses your naming rules. It still uses your formula writing rules. You're still going to have to be aware of all of those. We're going to be doing word equations. I mean, you're still going to have all of that stuff in the mix. So it's really important that all these things we've been learning in this unit that we have a really solid grasp on. And again, it's not going to end with the test next week on this. You have to have all of this stuff for all of the units that will come second semester. So out of all of our units this year, this is probably the most important unit as a whole. All right, so let's go ahead and get started. You have your notes in front of you, sort of like fill-in type, so we can get through this because it is quite a few different things we need to make sure that we cover today. So let's start with synthesis. Now, as the word synthesis insinuates, you've probably heard that word synthesize before. What's happening is you're having two or more reactants come together to make a single product. Okay, so you notice I underlined single product there because we're making one thing from two or more things. So again, that is synthesis. To synthesize means to come together. As a general form of the equation, we could make it look like this. Now, A and B are fictitious elements, okay, just any element from the periodic table. But if you had an element A plus an element B, you could make the compound of A and B together. Notice the plus sign's gone on the product side because they've come together to make a product now. Now, I said that it was an element A and an element B, but technically the A and the B that are on the reactant side can either be an element or a compound. So you could have a compound plus a compound making a new compound. That would still be synthesis. The key is that you only have one product here. If you make one product, then that is synthesis. And so A and B, these A's, this A and this B can either be elements or compounds, but then this one on this side has to be a compound. And cue music now. There we go. Hold on. There we go. It has to be a compound. Okay, so A, B has to be a compound made from A and B. So again, something plus something, either element plus element plus element, compound plus compound, making just a compound. So that is a synthesis type reaction. Let's go ahead and take a look at some examples. So the first one we're going to do is calcium and oxygen. So this is an element and an element. Remember, oxygen's diatomic, so that's why it says O2, but it's still an element plus an element. Now, as you could probably predict, the product that's going to form between these two is going to be calcium oxide. So we know the charge that calcium will take in a chemical formula when it's ionic is a +2. Oxygen has a -2. So when these two things come together, they're going to make CaO. So calcium had a +2 charge when it wanted to go into this compound. Oxygen gets a -2, so it's going to make CaO. Notice it's not balanced though, so one more quick step to balance it. We'll put 2's in front of the Ca and then a 2 in front of the product, and that would balance that equation out. Now, you may have needed to do that trial and error. You may have needed to do that math way. I'm not going to really focus on the balancing part in these examples, but I will show you excuse me. Now, if I was really good at video lessons, I would edit that out, but I'm not good at it. So I will show you the balanced ones on all of these just so that you get used to making sure that they're balanced, but we're not going to focus on the balancing part during this lesson. All right, so that's one that you should be able to predict the products because that's an ionic compound that forms from a metal and a non-metal. For this second example, I wouldn't make you do this one, predict the products in this one, but you should be able to look at the answer and tell that it is a synthesis. So when carbon dioxide and water come together, again, this isn't ionic, so it's not as easily done as just crisscrossing. So the product that forms is H2CO3. Again, you're not going to have to predict that, but you should be able to look at this second equation that's listed here and tell me that that's synthesis. And the reason why you know it's synthesis is because there is only one product. And this one is actually balanced already, all with ones. So again, the key to synthesis is that they're making only one product. That is a synthesis type reaction. Okay, so that is synthesis. Next one we're going to do is actually the exact opposite of synthesis. It's called decomposition. And as that word also infers, decomposition, or to decompose, means to break up into pieces. And that's what's happening in a decomposition reaction. If you have one reactant breaking into two or more products, that is decomposition. So again, one reactant making two or more products. So synthesis was one product, decomposition is one reactant. And just like synthesis, we can write like a general equation of AB yielding A plus B. So as you can see, it's breaking up. The AB still must be a compound, because in order to break up into two or more things, it had to have been made of two or more things. And then A and B on the product side can either be elements or compounds. So we can have a compound turning back into its elements, or we can have a compound turning into a compound and another compound, or we could have a compound turning into a compound and an element. There's lots of different options, lots of different combinations. Okay, but the key to decomposition is that there's only one reactant. Okay, if there's two reactants, it is definitely not decomposition. All right, let's look at some examples of these ones. So H2O. Now, some of these, if it's the compound decomposing into its elements, I expect you to be able to do. So for example, on this one, if I gave you this one and asked you what the products were that would form, you're decomposing this compound back into the elements it was made of. So the elements that water is made of are hydrogen and oxygen. But don't forget, hydrogen and oxygen are both diatomic, so they can't be by themselves. So if we write the products, it's going to be H2 and O2 are our products. Now you probably noticed right off the bat that it's not balanced. So we are going to decompose it into its elements, but then we're going to have to throw some coefficients on in front of the H2O and the H2 in order to balance this equation. So I do expect that you can do that type. If I give you a compound, I'm asking you to break it into its elements. Okay. Now here's an example of one that I wouldn't ask you to do. I could give you the answer and ask you what type of reaction it is, but I wouldn't ask you to do this one on your own, because CaCO3 doesn't break back up into its elements. It breaks that up into two compounds, and those compounds are CaO and CO2. So for this one, I would expect you, and this one is balanced, you can see that, I would expect you to be able to look at this equation, the second one that I've given you here, and tell me that that's decomposition. I wouldn't expect you to tell me how to make the products, but I would expect you to be able to tell me that's decomposition. And the reason why you know is because it only has one reactant. So if you have one reactant becoming two or more products, definitely going to be decomposition. Okay? So that's synthesis and decomposition. Again, they're pretty much the exact opposite of each other. Synthesis, one product; decomposition, one reactant. And we're going to practice more of these equations together, actually. So we're going to do the notes on this today, and then tomorrow we'll do a bunch of example practice problems together so that we can make sure that you can predict the products on the ones that you're supposed to be able to predict. Again, this one I don't expect you to predict, but the one before it, I do expect that you're going to be able to do those ones. Okay. All right, let's move on to single replacement then. So single replacement, as the name is inferring, again, if you think of these names, they really help you remember which ones are which. Single replacement is when one thing is going to be replacing something else. So single being the one thing, and then replacing something else. So here's the technical lingo on it. It occurs when an uncombined element takes the place of an element that's part of a compound. Occurs when an uncombined element takes the place of an element that is part of a compound. So it looks something like this. So here's your uncombined element, okay, and here's your elements that are in a compound. So what's going to happen is A is going to come in and bump B out. So A bumps B out. Notice that A is with X now, and B is all by itself. The example I use for this is like a relationship, a boyfriend and girlfriend. Okay, please assume that this BX right here is a boyfriend and a girlfriend. Okay, the B is the boy, the girl is the X. And so let's say this girl is in a compound or in a relationship with a boy, and the boy is not the best of boyfriends. Okay, if he's not the best of boyfriends, and then all of a sudden she meets the A boy, who he is fantastic. He's an A, so he's an A boy. So A is going to come in and replace the B boyfriend. The girl's going to get rid of the bad boyfriend and replace him with the good boyfriend. And so now you see the girls with the good boyfriend, and now the bad boyfriend is all by his lonesome self. You see, boys? Life lesson. Be a good boyfriend, and then you won't be kicked to the curb. So that's essentially what's happening here, is it's bumping it out. And these reactions don't always occur. I'm only going to give you ones that do occur, but it's possible if the girl's already with a good boyfriend, then this won't happen. Okay, and that has to do with something called an activity series, that if compounds are already in the right combination, in a combination that makes the better pairing, then this reaction doesn't happen. And that's why things don't immediately react. Some things don't immediately react because they don't have a good situation. But in the case of if your X is with the worse of the two metals, the better one is going to be able to replace it. Okay, so that's what the formula looks like. Let's just clarify a few things. That where we have A and B alone, they are pure elements. Okay, so elements by themselves. BX and AX are going to be compounds, and they're usually ionic compounds. We will only use ionic ones because covalent ones are much more difficult and would be very difficult for you to be able to predict. And you should be able to do these types of predictions by the time we're done with these notes tomorrow. So a note, just kind of note in your head that AX and BX are going to be ionic compounds for our situations that we are going to be using. And very important, as you can see, because I did it in yellow, is that these are ionic. So you want to definitely be using your charges and balancing your charges. And again, we're going to practice a bunch of these tomorrow. I really want to be there for that part of it, but I need you to get the basic ideas down of each type of reaction. Okay, so that is what single replacement's all about. Let's look at some examples. Sorry. Oh, look, how exciting. See how important it is? I made it flip around. All right. All right. Come on, computer. Thank you. So examples of single replacement. So let's say we had Mg and CuSO4. So magnesium's the good boyfriend. Copper is the bad boyfriend that's actually with the girl, which is SO4. So SO4 is with this bad copper, and all of a sudden she meets magnesium, and it's love at first sight. So she's going to bump out the copper and put copper all by himself, and then magnesium will be in the compound with her. So you see copper is now all by itself, and the magnesium's in the compound. But remember the part I told you about balancing the charges. When this new compound was formed, I had to re-account for their charges. So we know sulfate is a -2. Look on the periodic table, you see magnesium's a +2. So +2 and -2 will end up canceling each other out, and you end up with MgSO4. So you do have to account for your new compound. Also notice copper by himself, this magnesium by himself, they don't have charges. You only have a charge if it's in an ionic compound, and then you use it to crisscross. So no charges are shown on those pure elements. Okay, they do not have a charge because they are not part of an ionic compound. Okay, so that's the first example. Here's another example. So we have Fe and CuSO4. So Fe is going to bump out the Cu. Metal always will bump out the other metal. So Cu will be by itself now, no charge on it. And FeSO4, so the Fe crisscross, we end up with SO4. This one was a little harder because iron's actually one of our variable charge metals. So I couldn't have asked you to predict this one because you can't tell based on this over here what charge it was going to have. So I actually wouldn't have asked you to predict this one because of that. But this is the product. So Fe's going to bump out Cu. Cu will be by itself and make FeSO4. And again, that one's balanced, so we don't have to do anything special with it. Now I want to show you this one. This is similar situation, but guys, those of you who have been wondering why I'm saying that you're the bad ones, okay, here's an instance of the other way around. So you have a non-metal here, okay, so our non-metals were our girls. metal is our boy, and so this is a boy with a non-metal girl. So what's going to happen if you have a non-metal here, it's going to come bump out the non-metal. So this is a guy with a bad girlfriend, and this is a good girlfriend, and so he's going to get rid of the bad girlfriend, make her be by herself, so iodine by herself, and then chlorine's going to come in here, and it's going to make a compound with potassium and chlorine. But remember that iodine is one of your diatomics, so iodine has to, although it's by itself, it has to be shown as I2, and then potassium had a +1 charge, chlorine has a -1 charge, so you crisscross and you get your KCl. And if you notice, this one is not balanced, so I do have to balance it. Oh, sorry about that. I do have to balance it. So it can happen with nonmetals too. So make yourself a little note somewhere off to the side on your single replacements that metals bump out metals and nonmetals bump out nonmetals. So metal bumps metal, nonmetal bumps nonmetal. You can't have a metal bump out a nonmetal because then you won't have an ionic compound anymore. Okay, it'd be 2 metals or 2 nonmetals if you did that. Okay, so that is single replacement, and we'll practice some more of those formula writing equations later. All right, double replacement. So in this case, you're going to have a double replacement going on, so 2 replacements happening at the same time. So these situations are going to be when you have all compounds. Okay, actually, let me show you. Okay, hold on. You got to write this down. So 2 compounds or ions with different compounds are replacing each other. And again, we're going to use this with ionic compounds, although it is possible with covalent. It's not as predictable. So I want to make sure that you can do them. So we'll be using ionic ones. So here's a formula equation, just a generic equation. So you see A is with X, B is with Y. So what's going to happen here is A and B are going to swap partners. Okay, I'm not going to use a relationship example with this because that could just get really weird. So we're just going to say that A and B swap partners. I actually have a very applicable example of this that I can tell you tomorrow. Just remind me, it's easier to do in person. But so A and B are going to swap partners. So you see that A is now with a Y and that B is now with X. Okay, A is with Y and B is with X. And remember, the metal always gets listed first, so that's why A and B are still in the front of each one of those compounds. And we'll see some examples of that here in a second. And again, I'm going to go through lots of examples with you tomorrow, show you how to do this, because you do need to be able to predict these products. So A and B are switching is the main thing that's happening there. But again, we have to balance our charges. Very, very important. If you're doing anything with ionic compounds, if they're getting a new partner, you have to figure out what their combination together is going to look like. Okay, so that is double replacement. Now some examples. So sodium chloride and silver nitrate, both compounds. So what's going to happen here is this sodium and this silver are going to swap partners. So silver is going to go with chlorine. Silver has a +1, chlorine has a -1. And sodium's going to go with nitrate. Sodium has a +1, nitrate has a -1. So when we crisscross, we're going to get NaNO3 and AgCl. Again, make sure the metals are listed first in your compounds. And that one is already balanced. Okay, so that is one example of a double replacement reaction. Another example, AgNO3 and ZnCl2. So zinc is going to go with nitrate. Silver is going to go with chlorine. So again, we have to look at charges. You've memorized that zinc has a +2 and nitrate has a -1. So when that forms a compound, it makes Zn parenthesis NO3 2. Silver has a +1. You memorized that one. Remember, those were the 2 that you needed to memorize. And chlorine has a -1. So that makes AgCl. And you might notice that this is not balanced. So there's your balancing. You need a 2 in front of AgNO3 and a 2 in front of AgCl. Okay, so another example of a double replacement reaction. So single replacement is element in compound, making an element in compound. Double replacement is compound in compound, making compound in compound. They're just swapping partners. Okay, so that is double replacement. Let's move on now to combustion, which you may have heard before. A lot of people think combustion just means to blow up, but in actuality, combustion means to react with oxygen. That's what combustion means. So the reactions we're going to be doing, the formulas we're going to be doing, are with what we call a hydrocarbon. A hydrocarbon is something that's made of hydrogen and carbon. so it will be covalent compounds, and it again, combustion's when they burn in oxygen, and they always produce the same products. These problems are super easy. As soon as you see that it's a combustion problem, a hydrocarbon reacting with oxygen, you immediately know your products. They're always carbon dioxide and water. It's just a matter of how much carbon dioxide and water is forming, and that's where the balancing part will come in. So let's look at some examples. There's not really a generic form of this because it's the same products every single time. So here's a hydrocarbon, carbon with hydrogens, doesn't matter what the proportion is, reacting with oxygen, so the product will be CO2 and H2O. Every single time, you don't have to worry about anything goofy, it's going to be CO2 and H2O. And it needs to be balanced. Oh boy, did I not balance it. Why wouldn't I have balanced it? I don't know why I didn't balance it. You might have a different example on your paper. I don't know. Okay, let's do this one. Not sure if you had a different example, and this one would need to be balanced because it is not balanced. So make yourself a note that it's not balanced. We'll come back to that later. Okay, so this one, C2H5OH. Again, notice hydrocarbon. There's also some oxygen and hydrogen in it, or extra hydrogen, but it doesn't matter. It's got hydrogens and oxygens and carbons. It's a hydrocarbon, and it's reacting with oxygen. So the products, CO2 and H2O. Well, hello, there is the balancing on the last problem. That was really weird. There you go. I don't know why I did that. All right, so back to the problem we're working on. This hydrocarbon with oxygen has to make CO2 and H2O. Okay, and then in terms of that one's balancing, my computer is not happy with me. So in terms of that one's balancing, it looks like this. So C2H5OH plus 3O2 yields 2 CO2 plus 3 H2O. Okay, so that is combustion. Again, combustion ones are the easy ones because the products are always the same. Balancing, I would definitely go the math way on a combustion problem because usually the coefficients are a little goofy. Not always, as you can see with these ones, they're not terrible, but they can be. These are the ones that get those weird coefficients I was talking about the other day. Okay, so combustion. Last type, acid-base reaction. We're going to talk about acids and bases a lot second semester, but they want you to know about the type right now, so we're just going to do a real simple little explanation. Obviously, it's an acid and a base that are reacting, but you haven't really learned about what makes something acidic or basic. So here's going to be your trigger points. This is how you're going to know. If you have an acid, it's going to be a compound that starts with H, like HCl. H2SO4, HBr. There are, of course, exceptions, like water, H2O starts with H, but you know water. H2O2, hydrogen peroxide is another one. But if you see in your formulas anything that starts with an H, it's going to be an acid. And then the base will be the second reactant, and it will end in an OH. Bases typically end in hydroxide. So if you have a compound that starts with an H, and then another compound that ends in OH, then that is an acid-base reaction. And they always form the same two things, something called a salt, which is not just the stuff that you put on your food at home, and water. So let me show you what this one looks like. So here we start with a hydrogen compound, so this is an acid, ends with hydroxide, so this is a base. So an acid plus a base. So what's going to happen is this H and this OH are going to come together to make water. H and OH would be H2O, right? 2 hydrogens, 1 oxygen. So the potassium and the chlorine are going to make the salt. Now again, it's an ionic compound, so potassium has a +1, chlorine has a -1. So our products would be KCl, again coming from this K and this Cl, and then water, H2O. So this hydrogen and that hydroxide makes the water. So you're going to take and make water from your hydrogen and hydroxide, and then the other two are going to be made into an ionic compound. And the metal always goes first. Okay, metal always goes first. And that one is balanced already, so we don't have to do anything else with that one. This is another example. So it starts with an acid. It starts with an H, so it's an acid. Ends in hydroxide, so it's a base. So the H and the OHs, doesn't matter how many you have, are going to make water. The Mg and the F are going to form your salt. But magnesium has a +2 charge, fluorine has a -1. So when you crisscross those, you get MgF2 and then plus H2O. And that one we are going to need coefficients to balance. So you should have a 2 in front of HF and a 2 in front of H2O. And again, we're going to do some example problems with this. I will go through this process again. For right now, really the key to today's part of the lesson is understanding and being able to look at an equation and tell what it is, whether or not it's synthesis, decomposition, single replacement, double replacement, combustion, or acid and base. So let's real quick go through and kind of think about what made it stand out as being each of these types. So let's start with synthesis. For synthesis, one product was what you were looking for. Okay, for synthesis, one product was your indicator. For decomposition, one reactant was your indicator. If you saw only one reactant listed, that was going to be decomposition. For single replacement, both the reactants and the products had an element and a compound. So if it's element and compound, making element and compound, then that is single replacement. For double replacement, it's two compounds forming two compounds. So compound plus compound, making compound plus compound. For combustion, and actually I don't like this. Hold on. We're going to adjust this if I can get this stupid computer. No, it's not what I want. What are you doing? Okay. We're going to adjust this. So for combustion, I want you to write hydrocarbons plus O2 yielding CO2. Okay? Because technically, it needs to be O2 to be combustion, so I didn't like the way that was written. So hydrocarbons plus O2 yielding CO2 and H2O. And you may have a certain number of carbon here, you may have a certain number of hydrogen, just as long as it has hydrocarbons. Okay, let's go back to full screen. Okay, so combustion. And then for an acid-base reaction, one of your reactants starts with an H, that's the acid, and the other ends in OH, that's the base. Okay, so that's your major components that are going to tell you whether or not you've got synthesis, decomposition, single replacement, double replacement, combustion, or acid-base reactions. And again, tomorrow we'll run through a whole bunch of examples. But for now, what I want you to do is look back at your notes and think about what's on the screen right now. And if there's anything you're not sure about in how these are set up, then you need to make yourself a note so that tomorrow, when we're doing the examples, we can clear up any of the conceptual stuff as well. Okay, so Herr Hansen will tell you what you are doing from here on out, and please enjoy the rest of your day. Adios.